All right, we are going to cover exponential functions and logarithmic functions. We're actually starting with 5.2. If you have any interest in going back and looking at inverse functions, then I would suggest going back to 5.1, but that is not required for homework or for quizzes. Okay, section 5.2 has to do with exponential functions and their graphs. So we're going to graph exponential equations and their functions, and we're going to solve applied problems involving exponential functions and their graphs. All right, this book talks about the function of f of x having an a to the x. You will find in other books that it may be written as a times b to the x, where b is the base and a is a coefficient out front. Now, in this case, this chapter for you guys is not going to have a coefficient in front of the base. It's always going to be a 1. So that's why this also works. But I want to make sure people are aware that it can have this. All right? Okay. So the deal is this. Your x has to be a real number. The base has to be greater than 0, and it cannot equal 1. And the reason it can't equal 1 is because if you multiply 1 by itself however many times, you just get 1. All right? The reason we insist on the base being greater than 0 is because we don't want complex and imaginary numbers as a result. All right? So the following are examples of exponential functions. We have f of x equals 2 raised to the x, and we have f of x equals 1/2 raised to the x, and we have f of x equals 3.57 raised to the quantity of x minus 2. Now that x minus 2 is going to have us do something as it does when we have like our quadratic function or so on. Those things they're going to shift a bit, but they are not, there's nothing wrong with them being as they are, okay? They're completely valid as they are. All right, so when we take a look, here we want to know what our y is when we raise our 2 to the x. Well, we pick our x. But we're going to pick easy numbers. I generally encourage people to go from -2 to +2 or somewhere in that ballpark. This particular graph or chart we use +3 and -3. So we've got something all the way in between those. So for our 0, anytime you have anything other than a 0 raised to the 0 power, it's going to be a 1. I'm going to point something out here in just a second, but I want to make sure that we're really clear on this. For our purposes, when we have a to the x, anytime that x is 0, your a to the x is going to be 1. That's the result. Now, having said that, and again, we're not talking about it from the standpoint of if we have something other than a coefficient. You guys are not going to have to worry about it. I just want you to be aware that this can happen. So when you have a case where you have a b to the x, and if we say, okay, we don't know what a is, we need to figure it out. The way to go about doing that is to raise a times b to the 0, which is the same as a times 1, which is the same as a. So if you ever have a case where you have a coefficient out front and you want to know what's going on, you want to know what that coefficient is, here is the way you do it. You set it that x equal to 0, and then you solve for the a. You find out what a is and go from there. Otherwise, if you have just a 1 as a result, we know that our a is a 1 and that our base is whatever value raised to the 0 power. All right, so when we have our next one, we go something to the 1. Remember, we don't normally talk about, 5 to the 1st power. Well, 5 to the first power is just 5, right? We don't normally write it out that way. So here I have a 2 raised to the first power, which is just a 2, right? So we're going to go up like that. We're going to keep going. We've got our 2 squared, 2 cubed. Then we're going to have our negative exponents, right? Now keep in mind, when I have a negative exponent, what is that telling me? If I have a 1/2, I can write that as 2 to the negative 1, because I'm saying this thing does not live in this part of the numerator, or this part of the fraction. It's in the denominator. It doesn't really live in the numerator. So in this case, it's just going to, you're taking the inverse, right? You're going to take this is a, you'd have this as being a 1 over 1 and a 2 over 1 and a 4 over 1 and an 8 over 1. This is kind of the reciprocal of this. You're going to have the 1 over 2, 1 over 4, 1 over 8. All right. And hopefully that's really clear. If that's not clear as to why that is, be sure to get in touch with me. All right. So in the case of a growth exponential function, as x increases, your y is going to increase, and it goes forever and ever and ever and always. You have a lower bound, right? Our lower bound on our range, right? We're talking about this distance here. It goes from 0, unless we've modified it somehow to move it up or down, it goes from 0 all the way up to positive infinity, right? That's going to be our range. The domain can be all real numbers, right? But when we have this, it's going to increase. It's going to be going up quicker and quicker and quicker the further along we go. The bigger our x gets, the bigger, the steeper it's going to, your function is going to behave. Okay? So, when we have our, I talked a little bit about this, we have an asymptote here. We will approach 0, but we never get there. We get smaller and smaller and smaller. It never crosses it. It never even touches it. Okay? It gets really close, and you can keep zooming in, and it will never give you an ending. It will not ever touch 0 for you. All right, I'm actually going to pause this here, and we'll pick up here in just a bit.